What if everything we thought we knew about the universe was just the tip of the iceberg? Picture this. You look up at the night sky, and those countless stars seem to stretch endlessly in every direction. But what if that's just an illusion? What if the universe isn't some vast, uncharted expanse, but something far more mysterious, something with a shape we can barely comprehend? The truth is, the universe's true form is one of the greatest unsolved puzzles in science, and the answers might be stranger than anything we've ever imagined. For centuries, we've assumed the cosmos is infinite, flat, and ever-expanding, a cosmic canvas without edges. But what if it's not? What if it's curved like a giant sphere or twisted into a mind-bending donut? What if multiple universes are stacked like pages in a book or woven together in dimensions we can't even perceive? Scientists have spent decades chasing clues, from the faint echoes of the Big Bang to the way galaxies move in the void, and what they've uncovered challenges everything. The universe might be a shape-shifting enigma, and today we're diving deep into 30 of the most astonishing theories about its true form. This isn't just about abstract ideas, it's about rewriting our place in the cosmos. If the universe has a shape, it changes how we understand time, space, and even reality itself. Some theories suggest we're living inside a cosmic hologram. Others propose that the universe is a vast, looping ribbon, folding back on itself in ways that defy logic. And then there are the whispers of hidden dimensions, where gravity leaks into other realms, or where parallel versions of us exist just out of reach. Each of these ideas is a piece of a puzzle that could redefine existence as we know it. So buckle up, because by the end of this journey, you might never look at the night sky the same way again. One of the most widely accepted ideas about the universe's shape is also the most deceptively simple. It might be flat. Not flat like a piece of paper, but flat in the cosmic sense, meaning space itself doesn't curve back on itself or warp in unexpected ways. This theory comes from decades of studying the cosmic microwave background, the faint afterglow of the Big Bang. When scientists mapped its tiny temperature fluctuations, they found something startling. The patterns matched what you'd expect if the universe had no overall curvature, just like an endless, unbroken plane stretching forever in all directions. Think of it this way. If you could draw a giant triangle between three distant galaxies, the angles would add up to exactly 180 degrees, just like they do in a high school geometry textbook. That's the hallmark of Euclidean space, where parallel lines never meet, and the rules we learned in math class hold true on the grandest scale. But here's where it gets mind-bending. A flat universe doesn't just mean space goes on forever. It also suggests the cosmos will keep expanding indefinitely, growing colder and more diffuse until even the last stars flicker out. There are consequences to this idea. If the universe truly is infinite and flat, then somewhere out there, in a distant corner of space, there could be an exact copy of you reading these very words. In an endless expanse, every possible arrangement of matter must repeat eventually, meaning doppelganger galaxies, planets, and even people could exist unimaginably far away. But the flat universe theory isn't just about wild possibilities, it's rooted in hard data. The Planck satellite's measurements of the cosmic microwave background have placed tight limits on any curvature, and so far, the evidence points overwhelmingly toward flatness. Yet even this seemingly straightforward idea hides mysteries. Why is the universe so perfectly balanced between curvature and flatness? Some physicists argue it's no accident that inflation, the rapid expansion of the early cosmos, stretched space so thin that any initial wrinkles were smoothed out like wrinkles in a bedsheet. Others wonder if we're missing something. Could there be subtle curvatures at scales too vast for us to measure? Or might the flatness be a temporary state with some deeper structure waiting to be uncovered? The answers could redefine not just the shape of space, but the ultimate fate of everything in it. Now let's take a sharp turn away from the infinite flat plane and consider something entirely different. What if the universe isn't endless at all? What if it's curved into a colossal sphere, a closed loop of space where every direction eventually bends back on itself? Imagine the entire cosmos as a three-dimensional version of a balloon's surface. Just as a tiny ant crawling on that balloon could walk forever without ever finding an edge, we might be racing through space, unaware that our seemingly straight path is actually a giant cosmic circle. This spherical universe theory isn't just poetic. It comes from the math of Einstein's general relativity. If there's enough matter and energy in the cosmos, space itself could curve so dramatically that it closes like a loop. Think of it like this: if you shot a laser beam straight ahead in a spherical universe, and if you waited long enough, billions upon billions of years, that beam might eventually return to you from behind. The same could be true for entire galaxies. Travel far enough in one direction, and you'd end up right back where you started, like circumnavigating the Earth on foot, but on a scale so vast it defies comprehension. The implications are staggering. A spherical universe wouldn't just be finite, it would mean there's a cosmic limit to how far we can ever go. No infinite horizons, no endless copies of ourselves out there, just a vast but contained expanse where every journey loops back like an interstellar Möbius strip. Some scientists even speculate that if the universe is spherical, we might eventually spot ghostly duplicates of galaxies as light bends all the way around the cosmos, like seeing distant mountains reflected in a curved mirror. But here's the twist: if the universe is spherical, why doesn't it feel that way? Why does space seem so vast and uncurved? The answer lies in scale. A balloon looks flat if you're an ant standing on just a tiny patch of it. Likewise, our observable slice of the universe might be too small to detect the curvature directly. Yet subtle clues might still hide in the cosmic microwave background or the way galaxies cluster across the sky. Some observations even hint at unexpected patterns, like the universe appearing slightly closed in certain measurements, though the evidence isn't conclusive yet. Could we ever prove this theory? If the universe is spherical, future telescopes might spot faint echoes of distant galaxies appearing in multiple places at once, like flickers of the same cosmic candle seen from different angles. Or perhaps we'll detect subtle warping in the fabric of space itself, a gentle curve written into the oldest light in existence. Either way, this idea forces us to confront a humbling possibility. The universe might not be an endless frontier, but a vast celestial globe holding us all within its unseen, unimaginable walls. But what if the universe isn't a sphere or a flat plane? What if it's shaped like a cosmic donut? Welcome to the toroidal universe theory, where space isn't just curved, it's twisted into a giant looping ring. Picture this: the entire cosmos as a three-dimensional version of a donut's surface, where traveling far enough in one direction would bring you right back to where you started, but from the opposite side. It sounds like science fiction, but this bizarre shape could actually explain some of the strangest patterns we see in the night sky. The math behind this idea comes straight from topology, the study of shapes and how they connect. In a toroidal universe, space isn't infinite, it's finite but boundless, like a video game world where exiting one edge instantly teleports you to the other. This means light could wrap around the universe multiple times, creating eerie repetitions in our observations. Imagine spotting the same cluster of galaxies in two different parts of the sky. Not because they're twins, but because you're seeing the same cluster from two different angles as light loops around the cosmic donut. Some researchers even argue that odd symmetries in the cosmic microwave background, those faint heat patterns from the Big Bang, could be echoes of this twisted geometry. Here's where things get even wilder. In a torus-shaped universe, the very fabric of reality would play tricks on us. Gravity might behave differently along the curves of the donut, subtly altering how galaxies move in ways we're only beginning to model. Time itself could get tangled in the loops, with particles potentially interacting with their own past or future versions. And if space really is knotted this way, it might solve one of cosmology's biggest head-scratchers: why the universe appears so finely tuned for life. A torus naturally creates repeating regions with similar conditions, making luck less of a mystery and more of a geometric inevitability. But how would we ever prove something this unconventional? Astronomers are already hunting for clues. If the universe is toroidal, we might eventually detect duplicate patterns in galaxy distributions, like finding the same cosmic fingerprint stamped across distant parts of the sky. Others are scouring the cosmic microwave background for matched circles, pairs of spots with identical temperature variations that could be opposite views of the same ancient light, bent around the donut's curves. So far, no smoking gun has appeared, but the search reshapes how we see the cosmos. Whether a glitch in the data or a glimpse of truth, these hunts remind us the universe's shape might not just be hidden in the vastness of space, but in the invisible folds of its geometry. Now let's bend our minds around a universe that doesn't curve inward like a sphere or stay flat like a tabletop, but instead flares outward like a cosmic saddle. This is the hyperbolic universe, a shape where space itself curves away in all directions, creating a landscape where parallel lines don't just drift apart, they flee from each other at an accelerating rate. Picture riding a horse on an infinite saddle so vast that every step forward makes the horizon stretch wider, the ground dropping away beneath you in all directions. That's the unsettling beauty of hyperbolic geometry, and if it describes our cosmos, reality is far stranger than we thought. The math behind this idea is both elegant and unnerving. In a hyperbolic universe, the angles of a triangle add up to less than 180 degrees, the exact opposite of a spherical cosmos. Draw 3 lines between distant stars, and they'd bow outward like spider silk stretched to breaking point. This curvature would mean space isn't just expanding, it's doing so with a built-in urgency, pushing galaxies apart faster than gravity can rein them in. The consequences ripple across cosmology, infinite in volume yet endlessly diverging. A hyperbolic universe would make certain cosmic mysteries even harder to solve, like why distant supernovas appear to be accelerating away from us at speeds that defy expectations. But here's where it gets truly paradoxical. If space is hyperbolic, the farther you look, the emptier the universe becomes. Galaxies would thin out so drastically that distant civilizations might never spot one another, lost in an ever-widening web of curved void. Some theorists even suggest this could explain the Fermi paradox, the eerie silence of the cosmos. Not because life is rare, but because the shape of space itself scatters it beyond hope of contact. Yet for all its bleak implications, a saddle-shaped universe might also hold a key to one of physics' biggest puzzles: dark energy. That mysterious force driving cosmic acceleration could simply be the natural byproduct of space's inherent curvature, woven into the fabric of reality from the beginning. Detecting this curvature, though, is like trying to measure the bend of a continent while standing on a single grain of sand. Our observable patch of the universe might be too tiny to reveal the larger warp, but there are tantalizing hints. Certain anomalies in the cosmic microwave background, like unexpectedly large voids in galaxy distributions, could be fingerprints of hyperbolic geometry. Others argue that if space is curved this way, we might find subtle distortions in the apparent sizes of ultra-distant objects, as light snakes through warped space like a funhouse mirror. Until we peer deeper into the abyss, the saddle remains a ghost in the equations, a shape that could rewrite the rules of existence or vanish into the noise of cosmic data. Either way, it forces us to confront a profound question. Is the universe's true form not just hidden in its expanse, but in the invisible tension between its curves? What if everything around you, every star, every atom, even your own hands, wasn't truly three-dimensional at all? This is the startling premise of the holographic universe theory, where our entire cosmos might be nothing more than a flickering projection from a two-dimensional surface, like a cosmic movie screen playing the ultimate illusion. The idea sounds ripped from science fiction, but it emerges from the deepest puzzles of black holes and quantum mechanics, forcing us to rethink the very nature of reality. At the heart of this theory lies a paradox about information. When matter falls into a black hole, it seems to vanish forever, violating a fundamental law of physics: information can't be destroyed. But in the 1970s, physicist Jacob Bekenstein made a revolutionary discovery. He realized a black hole's entropy, a measure of its hidden information, isn't determined by its volume but by its surface area. It's as if all the data about what's inside gets compressed onto the event horizon's edge, like a celestial hard drive. Decades later, string theorists took this further, suggesting the entire universe might work the same way. The three-dimensional world we experience could be a holographic projection from a flat, two-dimensional boundary we can't perceive. Imagine the universe as a giant cosmic credit card. The embossed numbers feel three-dimensional under your fingers, but they're just raised patterns encoded on a flat surface. In the same way, the depth, texture, and movement of our reality might be an intricate illusion, with all the true data stored on a distant, unimaginably vast surface. This would mean every event in history, every particle interaction, is just shadow play, a dynamic hologram generated by quantum bits we'll never see directly. Even your thoughts and memories could be part of this grand projection, etched onto the fabric of space-time at its most fundamental level. The implications ripple through physics. If the holographic principle is true, it could unify Einstein's gravity with quantum mechanics, two frameworks that have stubbornly resisted reconciliation. It might also explain why the universe appears so finely tuned for life, because the rules coding our reality were written in a simpler, lower-dimensional language. Some researchers even speculate that glitches in this cosmic projection could account for quantum weirdness, like particles being spookily connected across vast distances. After all, if two seemingly separate objects are just pixels on the same underlying surface, their entanglement isn't so mysterious anymore. But how do you test something this radical? Scientists are hunting for clues in the noise of the cosmos. If space-time is pixelated like a hologram, there should be a fundamental limit to its resolution, a smallest possible grain size to reality. Some experiments are probing the blurring of distant gamma-ray bursts, looking for signs that space itself gets fuzzy at microscopic scales. Others analyze the cosmic microwave background for anomalous patterns that might betray a hidden code. So far, the evidence is circumstantial, but the pursuit reshapes our questions. Whether the universe is truly a hologram or not, the theory reminds us, reality's deepest layers might not be places we can visit, but information we're only beginning to decode. What if our universe isn't the only one? What if it's just a single bubble in an endless cosmic foam? That's the mind-bending premise of the multiverse theory, where our entire reality might be one of countless others, each with its own unique shape, laws, and even versions of history. Picture an infinite ocean of expanding space, where new universes constantly blink into existence like bubbles in a boiling pot. Some spherical, some flat, some twisted into shapes we can't even describe. This isn't just speculation, it's a serious scientific idea with roots in two of physics' most profound frameworks: eternal inflation and string theory. Eternal inflation suggests that the Big Bang wasn't a one-time event but part of an endless cycle. Space is expanding everywhere, but in some regions it slows down, forming stable universes like ours. In others, it keeps stretching exponentially, spawning new universes with every fraction of a second. Each of these bubble universes could have wildly different properties, like the density of matter or the strength of gravity. Some might collapse instantly, while others endure for trillions of years. And here's the kicker: their shapes could vary just as dramatically. One might be a perfect sphere, another a hyperboloid, and another a torus, each geometry locked in from the moment of its birth. String theory adds another layer of strangeness. It proposes that the fundamental building blocks of reality aren't particles but tiny, vibrating strings, and the way they vibrate depends on the shape of hidden extra dimensions. These dimensions could be curled up in countless configurations, each creating a unique universe with its own physics. Some versions might have 10 dimensions, others 7, others none at all. The sheer variety is staggering. Some estimates suggest there could be 10 to the power of 500 possible shapes, a number so vast it dwarfs the atoms in our observable universe. Imagine standing at the edge of our cosmic bubble, peering into the froth beyond. Other universes might be drifting just out of reach, separated by expanses of space where the rules are so alien, light itself couldn't cross. Some theorists even speculate that if two bubbles collided, the impact could leave scars in our cosmic microwave background, ghostly imprints of a neighboring universe brushing against ours. Others wonder if black holes are gateways to these other realms, their singularities warping space so severely that they puncture through to another bubble entirely. But how do we test something so inherently untouchable? Some scientists are scouring the cosmic microwave background for anomalous patterns, circular bruises, or strange temperature gradients that could hint at a long-ago collision with another universe. Others are simulating bubble universes in supercomputers, studying how they form, evolve, and interact. And then there's the philosophical angle. If the multiverse is real, it could explain why our universe seems so finely tuned for life. With infinite variations, some are bound to have the perfect conditions for stars, planets, and conscious beings to emerge. The multiverse theory forces us to confront a humbling possibility. Our universe might not be special, just one of countless experiments in a cosmic lab we'll never see. Yet it also offers a breathtaking vision of reality's richness, where every shape, every law, every possible history plays out somewhere in the void. Whether it's true or not, the idea reshapes how we see our place in existence, not as the center of everything, but as a single note in an infinite symphony of universes, each singing its own shape into the dark. What if the universe isn't just born once but dies and rebirths endlessly, like a cosmic phoenix rising from its own ashes? This is the spine-chilling idea behind the cyclic universe theory, a vision of reality where expansion and collapse aren't the end, but just phases in an infinite loop of creation. Imagine a cosmos that doesn't begin with a single big bang but with a big bounce, a moment where a previous universe's collapse becomes the seed for our own. And with each rebirth, the universe could twist into a new shape, one cycle a flat plane, the next a knotted torus, another a hyperboloid, as if reality itself is constantly reinventing its geometry. The math behind this idea is as elegant as it is profound. Einstein's equations originally suggested the universe must either expand or contract, but they didn't rule out the possibility of a rebound. Modern quantum gravity theories take this further, proposing that when a dying universe collapses to an unimaginably dense point, quantum effects could prevent total annihilation. Instead of a singularity, there's a repulsive force, a cosmic trampoline that launches a new expansion. This isn't just recycling matter, it's recycling space-time itself, with each cycle potentially shuffling the fundamental constants of physics like a deck of cards. Here's where it gets even wilder. If the universe cycles endlessly, traces of past iterations might linger in the fabric of our own. Some theorists suggest that subtle anomalies in the cosmic microwave background, those faint heat patterns from the Big Bang, could carry imprints of a pre-bounce universe like scars from a life before. Others speculate that dark energy, the mysterious force accelerating our expansion today, might be the residue of a previous cycle's death throes, a kind of cosmic exhale before the next inhale begins. But how could a universe's shape change between cycles? Picture a balloon deflating to a tiny point, then reinflating, but this time twisted into a different form. The forces at play during the bounce could warp spacetime's geometry unpredictably, like crumpling a piece of paper into a ball, then smoothing it out with new creases. One cycle might leave space flat, while the next introduces curvature from gravitational waves or exotic matter we can't yet imagine. This means the laws we take for granted, like the speed of light or the strength of gravity, might not be eternal truths but local conditions, temporary rules in an endless game of cosmic regeneration. The implications rewrite our place in time. If the cyclic model is real, everything we see, galaxies, stars, even our own existence, might be just one verse in an infinite epic, with civilizations rising and falling across cycles we'll never witness. It's a humbling thought. The universe could have died 1,000 times before us and may die 1,000 times after, each collapse not an end but a doorway. And somewhere in the geometry of those rebounds might lie the answer to the deepest question of all, not just what shape the universe is, but how many shapes it's been. Now imagine a universe shaped like a cosmic soccer ball, a vast 12-sided die tumbling through the void. This is the startling vision of Poincaré's dodecahedral space, a theory where the cosmos isn't flat or spherical but folded into a giant geometric puzzle. The idea comes straight from the math of topology, where a dodecahedron, a 12-faced shape with pentagonal sides, can be stitched together in a way that creates a finite but edgeless universe. Travel far enough in any direction and you'd loop back to your starting point, but with a twist literally. Light would weave through the folds in bizarre ways, creating ghostly repetitions in the sky that could explain some of the most puzzling patterns in the cosmic microwave background. The clues first emerged in the early 2000s when astronomers studying the afterglow of the Big Bang noticed something odd. The largest scale fluctuations in temperature, those faint ripples from the universe's infancy, weren't as pronounced as expected. It was like listening to a symphony but finding the deepest bass notes mysteriously muted. This anomaly, known as the low quadrupole, defied standard cosmic models. But a dodecahedral universe could explain it. If space is folded into this 12-sided shape, certain wavelengths of energy would naturally cancel each other out as they wrap around the structure, dampening the cosmic hum in just the way we observe. Here's where the geometry gets hypnotic. A dodecahedral universe isn't just a static shape, it's a hall of mirrors on a cosmic scale. Light traveling through it would take multiple paths, meaning a single galaxy could appear in 5 different places in the sky, each image twisted like reflections in a kaleidoscope. Some researchers even speculate that the famous cold spot in the cosmic microwave background, a chillingly empty region spanning billions of light years, might be a glitch in this celestial mirror maze where light gets scrambled by the folds of space itself. But how could something as angular as a dodecahedron describe the smooth, vast cosmos we see? The answer lies in scale. Just as a soccer ball's surface feels curved when you're an ant crawling across it, a dodecahedral universe would appear locally flat to us. Only on the grandest scales would the angles reveal themselves, like standing on a mountain and finally seeing the curve of the Earth. Proving this, though, is like trying to discern the shape of a room while locked inside it. Scientists have hunted for matching circles in the cosmic microwave background, telltale pairs of identical patterns that would signal light wrapping around the dodecahedron's faces. So far, the evidence is tantalizing but inconclusive, leaving this geometric ghost hovering at the edge of discovery. What's mesmerizing about this theory isn't just its elegance, but its audacity. A dodecahedral universe would mean reality has a hidden symmetry, a mathematical purity echoing through the chaos of galaxies and dark matter. It suggests the cosmos isn't just a random expanse, but a structured, almost artistic creation, one where the answers to our deepest questions might be written not in equations alone, but in the silent, shimmering angles of space itself. Whether the universe truly is a cosmic dodecahedron remains an open question, but the possibility reminds us, sometimes the grandest truths hide in the simplest shapes. What if the universe isn't just vast? What if it's endlessly intricate, a cosmic tapestry where the same patterns repeat at every scale, from the smallest quark to the largest supercluster? This is the mind-bending premise of the fractal universe theory, an idea that suggests reality is built like an infinite Russian nesting doll, with structures mirroring themselves across dimensions. The concept traces back to mathematician Benoit Mandelbrot, who revolutionized our understanding of complexity by revealing how simple rules could generate infinitely detailed shapes, fractals, where zooming in or out reveals the same patterns ad infinitum. Now imagine applying that to the cosmos, the branching veins of a leaf, the turbulent swirl of a galaxy, and the distribution of matter in the universe might all follow the same hidden blueprint. The evidence starts with the large-scale structure of the cosmos. When astronomers map the universe, they find galaxies clustered in filaments and voids, forming a cosmic web that looks startlingly similar to neural networks in the human brain or the branching roots of a tree. These patterns aren't random, they follow mathematical distributions that fractal geometry predicts. Take the distribution of galaxies, for instance. Whether you examine a patch of sky 1,000,000 light-years wide or 1,000,000,000, the clustering appears eerily consistent, as if the universe is stamped with the same signature at every magnification. Some researchers argue this isn't coincidence but a fundamental property of space itself, woven into the fabric of expansion from the Big Bang onward. But how could a fractal universe work? Picture a Mandelbrot set, a shape where every tiny portion, no matter how small, contains a distorted but recognizable copy of the whole. If space behaves similarly, then every galaxy cluster might contain miniature echoes of the entire cosmos, and every star system could mirror the grand design in ways we're only beginning to discern. This would mean the universe isn't just expanding, it's unfolding, recursively building complexity from simple rules. Even time might play by fractal rules, with cosmic processes repeating in cycles that echo across scales, supernova resembling quantum fluctuations, black holes mirroring atomic nuclei. The implications are staggering. A fractal universe would challenge our notions of infinity, suggesting that no matter how deep we probe, reality never simplifies. It could also solve one of cosmology's biggest puzzles: why the universe appears lumpy at every scale, with matter clumping in ways that defy traditional models. If spacetime is inherently fractal, then this unevenness isn't a bug, it's a feature written into the DNA of existence. Some theories even propose that dark matter and dark energy, those enigmatic forces shaping the cosmos, might emerge naturally from this recursive geometry, like shadows cast by a deeper, repeating structure. Yet for all its elegance, the fractal universe theory remains contentious. Critics argue that the apparent self-similarity in cosmic structures could just be a temporary phase, a snapshot of chaos that looks ordered from our limited vantage point. Others point out that true mathematical fractals require infinite complexity, something the real universe might not sustain. But proponents counter with tantalizing clues, like the way fluctuations in the cosmic microwave background align with fractal predictions, or how simulated universes with fractal rules spontaneously generate realistic galaxy distributions. Whether the cosmos is truly fractal or not, the idea reshapes how we see our place in it. If the universe repeats its patterns endlessly, then we're not just observers of its grandeur, we're participants in a cosmic recursion, where every atom and every galaxy is part of a rhythm older than time. And somewhere in that infinite repetition, the answers to existence might not lie in finding something new, but in recognizing the patterns we've seen all along. Einstein once believed the universe was eternal and unchanging, a perfect static cosmos where galaxies hung motionless in space like stars painted on a cathedral ceiling. This was his original vision, an elegant solution to his equations of general relativity in 1917, where the fabric of space-time neither expanded nor contracted but stood perfectly balanced. To make this work, he introduced the cosmological constant, a kind of anti-gravity force that counteracted the natural tendency of matter to collapse under its own weight. It was a universe frozen in time, a celestial clock that never wound down. But then, in the late 1920s, Edwin Hubble made a discovery that shattered this serene picture. Through the lens of the Mount Wilson telescope, he saw galaxies not as fixed lanterns in the void but as ships drifting away from one another, their light stretched redder with distance. The universe wasn't static, it was stretching like warm taffy, growing larger with every passing second. Einstein famously called his cosmological constant his greatest blunder, abandoning the idea of a static universe in the face of overwhelming evidence. Yet here's the twist: modern cosmology has resurrected the cosmological constant in a way Einstein never anticipated. That once dismissed fudge factor now plays a starring role in our understanding of dark energy, the mysterious force accelerating the universe's expansion. It turns out Einstein's static universe wasn't entirely wrong, just premature. His equations had glimpsed a deeper truth about spacetime's inherent energy, even if his interpretation of its role was off by billions of years. Some theorists now wonder, could a static universe exist under different conditions? Imagine a cosmos where the outward push of dark energy perfectly balances the inward tug of gravity, creating pockets of equilibrium within the larger expansion. Or consider models where the universe cycles through phases of expansion and contraction, briefly passing through static moments like a pendulum pausing at the top of its swing. Even more radical is the idea that our observable universe might be a rare bubble of imbalance within a vaster, static multiverse, an island of change in an otherwise frozen sea of reality. The irony is profound. Einstein's discarded idea now helps explain the very expansion that discredited it. And while we know the universe isn't static today, the concept lingers like a ghost in the equations, reminding us that even wrong theories can contain seeds of truth. Who knows, perhaps in some distant epoch, trillions of years from now, the cosmos will settle into the perfect balance Einstein once imagined, not as a timeless reality, but as the final sigh of an aging universe. Pick up a guitar and pluck one of its strings. The vibration creates a musical note, distinct and pure. Now imagine that the entire universe works the same way, but instead of sound, those vibrations create matter, energy, even space and time themselves. This is the essence of string theory, one of the most ambitious frameworks in physics, and it suggests the universe's true shape might be far more intricate than we ever dreamed. Hidden beneath the reality we perceive could be tiny, curled-up dimensions, geometric labyrinths so complex they dictate the very laws of nature. At the heart of this idea are shapes called Calabi-Yau manifolds, mathematical objects with 6 dimensions twisted into forms that make even seasoned theorists pause. Picture a hyperdimensional origami, folded in ways that allow strings, the fundamental threads of reality, to wiggle and vibrate in countless patterns. Each vibration produces a different particle, like a cosmic harp where one pluck creates an electron, another a quark. But here's the catch: the exact shape of these hidden dimensions determines how those strings vibrate, which in turn sets the rules for everything from gravity to the mass of a proton. A slight kink in the geometry could mean the difference between a universe bursting with stars and one too unstable to form atoms at all. Now, you might wonder, how do you visualize a 6-dimensional object? Think of it like this. Imagine standing in a forest where every tree is a 3-dimensional object. From a distance, the forest looks flat, like a 2-dimensional painting. Only when you walk inside do you perceive the depth. Calabi-Yau manifolds work similarly. At our everyday scale, those extra dimensions are rolled up, too small to detect, like the intricate grooves on a vinyl record that vanish when you step back. But zoom in close enough, and the richness of their structure becomes clear, governing the harmonies of the cosmos itself. the implications are staggering. If string theory is correct, the shape of these hidden dimensions could explain why our universe has exactly 4 fundamental forces, why the electron has its precise charge, even why time flows in one direction. Some versions of these manifolds might permit exotic physics, like particles moving faster than light or gravity leaking into other dimensions. Others could harbor entire shadow universes, nestled in folds too tight for our instruments to probe. And the most mind-bending possibility, there may not be just one true Calabi-Yau shape, but an astronomical number. Some estimates suggest 10 to the 500 variants, each birthing a universe with different laws. This is the string theory landscape, a vast cosmic garden where every flower is a possible universe, each with its own geometry and physics. Our universe might just be one bloom in that garden, its particular laws shaped by the accidental twists of its hidden dimensions. While we can't yet peer into those infinitesimal folds, physicists hunt for indirect clues like subtle patterns in particle collisions or gravitational waves that might betray their presence. Until then, the shapes we can't see remain the silent architects of everything we can. What if our 3-dimensional universe is just one slice of a much larger, higher-dimensional reality, like a sheet of paper drifting through an unseen cosmic library? This is the startling premise of the brane world scenario, a theory that reimagines existence as a 3-dimensional brane floating in a space with more dimensions than we can perceive. The word brane comes from membrane, and just as a 2-dimensional sheet exists within 3-dimensional space, our entire universe might be a 3-dimensional surface embedded in a vast multidimensional bulk. Here's the twist: while particles like light and matter could be trapped on our brane, gravity might not be. It could be leaking into the hidden dimensions around us, explaining why it feels so weak compared to other fundamental forces. Think of it like this: imagine ants crawling on a tightrope, unaware that the rope is suspended in a vast canyon. To the ants, their world seems one-dimensional. They can only move forward or backward. But if a gust of wind hits the rope, making it sway, they might feel a mysterious force they can't explain. In the brane world scenario, we're the ants. Gravity's puzzling feebleness, it's a trillion times weaker than electromagnetism. Could be because it spreads into extra dimensions, diluted like ripples fading across a pond's surface. The math behind this idea emerges from string theory, which suggests there could be up to 11 dimensions in total. Some of these dimensions might be compacted into tiny, curled-up shapes, but others could be vast, hidden realms parallel to our own. In certain models, our brane floats near others, separated by less than a millimeter in a higher dimensional direction we can't see. This raises spine-tingling possibilities, like parallel universes hovering right beside us, separated by a gap smaller than the width of a human hair, yet utterly invisible. Even more unsettling, if another brane collided with ours, it could trigger a cataclysmic event resembling the Big Bang, resetting the cosmos in a fiery rebirthing. How would we ever detect these hidden dimensions? Scientists have devised ingenious experiments to hunt for them. One approach involves measuring gravity at microscopic scales. If it deviates from Newton's inverse square law at tiny distances, it could betray the presence of extra dimensions, stealing gravitational force. Another looks for particles like gravitons, the hypothetical carriers of gravity, which might briefly vanish into higher dimensions before reappearing, leaving telltale gaps in particle collision data. So far, no smoking gun has been found, but the search reshapes how we see reality's fabric. The brane world scenario doesn't just tweak our cosmic map, it rewrites the rules. If true, it means the universe we see is a shadow of something far grander, with hidden dimensions orchestrating the forces we take for granted. It's a humbling thought: the weight of a planet, the arc of a falling apple, even the pull of a black hole might all be echoes of a reality we're only beginning to imagine. And somewhere beyond the edges of our perception, the true shape of existence could be waiting, vast and unseen, like an ocean around an island that doesn't yet know it's surrounded by water. What if our entire universe is hidden inside the belly of a monstrous black hole, a cosmic Russian doll where the crushing heart of one singularity births an entirely new reality? This is the spine-tingling premise of the black hole universe theory, a radical idea suggesting that the Big Bang wasn't the beginning of everything, but the moment our cosmos emerged from the wreckage of a collapsed star in some higher dimensional realm. Picture this: trillions of years ago, a massive star in a parent universe exhausted its fuel and imploded, compressing into a singularity so dense that space and time shattered. But instead of annihilation, that collapse sparked a new universe with physics reborn and dimensions rearranged. Our expanding cosmos, in this view, might just be the echoing aftermath of that primordial detonation, its shape sculpted by the black hole's hidden geometry. The math behind this idea is as elegant as it is unsettling. When matter collapses into a black hole, general relativity predicts that all its information, the particles, the forces, even the quantum states, gets crushed into an infinitesimal point. But quantum mechanics insists information can't truly be destroyed. The black hole universe theory bridges this paradox by proposing that the singularity doesn't erase information but reprograms it, birthing a new space-time continuum inside the black hole's event horizon. Think of it like a cosmic recycling plant. The crushed remnants of a dying star don't vanish, they reincarnate as the raw materials for an entirely new universe with its own laws and constants. Here's where the theory gets even wilder. The shape of our universe could carry fingerprints of that violent birth. If the parent black hole was spinning as most real-world black holes do, its rotation might have imprinted a subtle twist on space-time, leaving our cosmos with a preferential axis or large-scale asymmetries. Some researchers even speculate that dark energy, the mysterious force accelerating cosmic expansion, could be the lingering kick from that initial collapse, like a spring uncoiling across billions of years. And if black holes in our universe themselves contain nested universes, the structure of reality might resemble an infinite fractal, a cosmic matryoshka doll where every level hides another. But how would we ever prove we're living inside a black hole? Clues might lurk in the cosmic microwave background, the oldest light in existence. Anomalies like unexpected temperature variations or polarized light patterns could hint at an inherited spin from the parent singularity. Others hunt for evidence in the distribution of galaxies. If the universe has even a slight preferred direction, it might betray its origins as the interior of a rotating black hole. Then there's the enigma of dark matter. Some models suggest it could be gravitational shadows cast by objects in the parent universe, leaking through the singularity like echoes through a locked door. The implications rewrite our very notion of existence. If the theory holds, the black holes we observe today might not be dead ends. They could be cosmic wombs, each cradling a newborn universe with its own physics, its own stars, its own civilizations wondering, just as we do, where they truly came from. It's a humbling thought. Our entire history, from the first stars to the rise of life, might be unfolding inside an object some other universe considers a collapsed star. And one day, trillions of years from now, when our own cosmos grows cold and sparse, the black holes we've left behind may spark new realities of their own, an endless cycle of creation hidden within destruction, where every ending is secretly a beginning. What if our universe has a hidden twin, a perfect mirror image where time flows backward and matter is swapped for antimatter? This is the startling idea behind the mirror universe theory, a concept drawing from one of physics' most fundamental symmetries, CPT invariance. The letters stand for charge, parity, and time, three properties that, according to quantum field theory, must remain balanced for the universe to make mathematical sense. Flip a particle's charge, mirror its position, and reverse the flow of time, and the equations still hold. But what if this isn't just a mathematical quirk? What if there's an entire parallel cosmos where these transformations are real? Let's break it down. In our universe, electrons carry a negative charge. But in a mirror universe, they might be positrons, their antimatter counterparts with positive charge. Gravity could push instead of pull, and stars might form from the ashes of supernova rather than collapsing into them. Even causality might flip. An event's effect could precede its cause, like seeing a shattered vase reassemble before the cat knocks it off the table. At first glance, this sounds like science fiction, but the math suggests it's plausible. If you took every particle in existence, replaced it with its antiparticle, reflected it through an imaginary cosmic looking glass, and ran the clock backward, the resulting universe would obey the same fundamental laws. The implications are staggering. If a mirror universe exists, it could explain one of cosmology's biggest mysteries: why there's so little antimatter in our cosmos. According to the Big Bang Theory, matter and antimatter should have been created in equal amounts, annihilating each other instantly, yet somehow matter prevailed. A mirror universe could be the missing antimatter's hiding place, a shadow realm where our protons are their antiprotons and our stars are their anti-stars. Some physicists even speculate that the two universes could have been born together, like twins separated at creation, each compensating for the other's imbalances. But how would we detect something so inherently hidden? One clue might lie in neutrinos, those ghostly particles that barely interact with matter. Certain experiments have detected anomalies in how neutrinos oscillate between flavors, sparking theories that they might be leaking into a mirror dimension, flipping identities in ways we can't yet explain. Others hunt for gravitational echoes, subtle ripples in space-time that could hint at mirror black holes or stars tugging on our universe from the other side of the cosmic glass. The most mind-bending possibility: a mirror universe wouldn't just be a curiosity, it could redefine the arrow of time itself. If time flows backward there, then from their perspective, we're the ones living in reverse. Our future is their past, their dawn is our dusk, and the very idea of cause and effect becomes a cosmic question mark. Whether this mirror world exists or not, the theory forces us to confront a profound truth. The universe might not just be stranger than we imagine, but stranger than we can imagine, with every symmetry in physics whispering secrets about realities we've yet to see. What if our universe isn't a vast expanse of stars and galaxies, but an ultra-advanced simulation, a cosmic video game running on some unfathomable computer? This is the jaw-dropping premise of the simulation theory. An idea that reimagines reality itself as a digital construct, where the very fabric of space and time might be lines of code in a program beyond our comprehension. The theory gained serious traction when philosopher Nick Bostrom laid out a chilling logical argument. If civilizations inevitably develop the power to create hyper-realistic simulations of their ancestors, and if they choose to run countless such simulations, the odds are overwhelming that we're living inside one rather than the original, base reality. But here's where it gets even wilder. The shape of our simulated universe might not be a smooth, continuous expanse but a finely pixelated grid, like a Minecraft world scaled up to cosmic proportions. We already see hints of this in physics. At the smallest scales, space isn't perfectly smooth. It appears grainy, with a fundamental limit to how precisely we can measure position or energy. This is the Planck length, a distance so tiny that attempting to probe beyond it would require so much energy it'd collapse into a black hole. Some physicists interpret this as the universe's resolution limit, the pixel size of the simulation we're in. Imagine a video game where characters can't perceive the individual pixels on their screen. Everything looks seamless to them, but the underlying code operates in discrete chunks. In the same way, our reality might be rendered in quantum bits, with the apparent smoothness of space-time an illusion created by unfathomably small computational steps. Even the bizarre behavior of quantum particles, how they seem to exist in multiple states until observed, could be explained as processing optimizations, like a simulation only rendering details when a player looks at them to save computing power. The implications spiral into every corner of science. If we're in a simulation, the laws of physics might not be fundamental truths but programmed parameters, adjustable by whoever or whatever controls the system. Glitches could exist. Unexplained phenomena like dark energy or quantum entanglement might be artifacts of the code, shortcuts taken to keep the simulation running smoothly. Some researchers even propose deliberate experiments to test the theory, like hunting for rounding errors in high-energy particle collisions that might reveal the underlying computational grid. Yet the most haunting question isn't just whether we're in a simulation, it's what lies outside it. Is our universe one of billions running on some alien supercomputer? Are the programmers watching us, or have they forgotten their experiment entirely? And if we ever proved this was all a construct, would the simulation keep running, or would someone hit delete? The theory forces us to confront the unnerving possibility that the universe's true shape isn't a geometric form but a data structure, with every atom, every thought, just a flicker in an infinite cosmic calculation. Black holes devour everything: light, matter, even time itself. But what if the cosmos began with the opposite, a cosmic fire hose blasting energy and space into existence instead of swallowing it? This is the white hole, a hypothetical twin to the black hole, first imagined as a mathematical curiosity in Einstein's equations. Where a black hole's gravity is so strong nothing escapes, a white hole repels all matter, ejecting it violently into space like a cosmic geyser. And some physicists suspect these elusive objects might be more than just theory. They could be the secret architects of our universe, with the Big Bang itself being the ultimate white hole eruption. The math is eerily symmetrical. Just as a black hole forms when a massive star collapses into a singularity, a point of infinite density, a white hole would be the time-reversed version, exploding outward from a singularity. Picture a black hole's event horizon in reverse. Instead of a one-way membrane trapping everything inside, it becomes an impassable barrier keeping everything out, with matter and energy erupting from its core like sparks from a forge. Some quantum gravity models, like loop quantum cosmology, suggest that when a black hole's collapse reaches maximum density, quantum effects could trigger a bounce, transforming the singularity not into endless darkness but into a white hole's radiant birth. This leads to a breathtaking possibility. If our universe emerged from a white hole, it would explain the Big Bang's explosive energy without invoking a true beginning. Instead of a mysterious singularity appearing from nothing, our cosmos could be the afterlife of a black hole from another universe, a recycled reality, where the collapse of one world becomes the birth of another. The white hole's violent ejection would then manifest as our observable universe's initial fireball, with the cosmic microwave background being the cooled embers of that primordial detonation. But how would a white hole differ from the Big Bang we know? For one, it might leave fingerprints in the distribution of matter. A pure white hole explosion would be chaotic, potentially seeding the universe with irregular clumps of energy, patterns we might still detect in ancient light or galaxy distributions. Some researchers even speculate that certain anomalies in the cosmic microwave background, like unexplained cold spots or swirling polarizations, could be echoes of this turbulent birth. Others hunt for signs in high-energy particle collisions, searching for microscopic echoes of white hole physics that might briefly flicker into existence. The most radical implication: if white holes exist, they could be portals not just to other universes, but to other times. Since black holes warp space-time so severely that they bend the arrow of time itself, their white hole counterparts might spew matter not just into another space, but into another era entirely. This would mean our universe's past could be another reality's future, with time looping back on itself in ways that defy intuition. While no white holes have ever been observed, their theoretical lifetimes are likely fleeting, the idea reshapes how we see the cosmos. It suggests that the universe's grandest events might not be unique, but part of an endless cycle of collapse and rebirth. And somewhere out there in the cosmic shadows, other white holes might be erupting into new realities, each carrying the legacy of a black hole's death into the fire of another beginning. What if the Big Bang wasn't a singular explosion but a cosmic car crash, a shattering collision between two universes in a hidden, higher dimensional realm? This is the spine-tingling vision of the ekpyrotic universe theory, where the shape of our cosmos isn't born from fire but from a catastrophic encounter between vast, floating, branes, sheets of reality drifting through an unseen void. The name ekpyrotic comes from the ancient Greek for conflagration, and it's a fitting label for a model that replaces the traditional Big Bang with a spectacle of colliding dimensions, where our entire universe emerges from the wreckage like a phoenix rising from the ashes. The idea springs from string theory's most radical offshoots, which propose that our four-dimensional universe might be a three-dimensional brane, short for membrane, existing alongside others in a higher dimensional space called the bulk. Imagine two enormous sheets of paper floating parallel to each other in an endless dark room, each one an entire universe unto itself. Normally, these branes drift undisturbed, but if they ever collide, the impact could unleash enough energy to forge a new cosmos. In this scenario, the Big Bang wasn't the beginning of time, just the latest reset in an endless cycle of collisions, each one reshaping space-time like a cosmic etch-a-sketch. Here's where the geometry gets mind-bending. When these branes smash together, the energy doesn't explode outward in all directions like a fireball. Instead, it ripples through the fabric of the branes themselves, creating a hot, dense plasma that appears to us as the birth of a universe. The three-dimensional space we know might just be the aftermath of that collision, stretched and smoothed by the violence of the impact. And because the branes are flat, the resulting universe inherits their geometry, explaining why our cosmos appears so remarkably flat on large scales, without the curvature you'd expect from a traditional explosion. The implications rewrite cosmic history. Instead of a singularity spawning everything from nothing, the ekpyrotic model suggests a quieter prelude, a long, cold stretch where the branes drift closer and closer, their gravitational pull warping the space between them. This slow crash could solve one of the Big Bang's biggest puzzles: why the early universe was so uniform. Traditional inflation theory posits a rapid expansion to smooth out wrinkles, but the ekpyrotic universe doesn't need it. The brane's collision naturally evens out irregularities, like rolling over a crumpled piece of paper with a steamroller. But how could we ever prove such a wild idea? Some researchers hunt for gravitational echoes, subtle ripples in space-time left over from the pre-collision phase. Others look for unique patterns in the cosmic microwave background, like swirling polarizations or temperature anomalies that might betray the brane's gravitational tug-of-war. Then there's the question of cycles. If this has happened before, will it happen again? The theory suggests the branes might bounce apart after the collision, only to drift back together over eons, setting the stage for another cosmic rebirth. Our universe, then, could be one page in an endless cosmic flipbook, its shape reset with every collision. The ekpyrotic theory doesn't just challenge our origin story, it redefines the universe's very architecture. If true, the cosmos isn't a solitary expanse but a layer in a grander dimensional sandwich, its fate intertwined with unseen neighbors, and somewhere beyond the edges of perception, those other branes might still be floating, waiting for the next inevitable crash that will rewrite reality all over again. Roger Penrose, the Nobel-winning physicist who helped unlock the secrets of black holes, has a theory that redefines eternity itself. His conformal cyclic cosmology proposes that the universe doesn't have a single beginning or end. Instead, it's an endless loop of cosmic resets, where the distant future of one epoch becomes the Big Bang of the next. But here's the twist: these aren't just repetitive explosions in empty space. each cycle is connected through a process called conformal rescaling, a mathematical transformation that lets the infinite and the infinitesimal become interchangeable. Picture the universe stretching so vast and cold that all distances blur into meaninglessness, while particles lose their mass and time loses its grip. At that point, the entire cosmos becomes mathematically identical to a searing hot singularity, the exact conditions of a new Big Bang. It's not a rebirth from nothing, but a seamless metamorphosis, like a snake shedding its skin to reveal a fresh one underneath. What makes this idea so radical is how it handles infinity. In Penrose's model, the universe doesn't just expand forever or collapse back on itself. It reaches a state where scale itself becomes irrelevant. Think of a desert stretching to the horizon. From a distance, a single grain of sand and the entire dunes share the same smooth, undulating shape. Similarly, a universe devoid of stars, galaxies, or even protons, where only massless particles like photons remain, can be rescaled to match the tiny, hot chaos of a newborn cosmos. Gravity waves from colliding black holes in the previous cycle might even imprint faint patterns on the new universe's cosmic microwave background, like echoes whispering across eternity. The evidence: Penrose points to mysterious Hawking points in the sky, circular patches of polarized light in the cosmic microwave background that could be the afterglow of supermassive black hole collisions from a cosmos that existed before ours. These anomalies defy standard cosmological explanations, but in conformal cyclic cosmology, they're fossils from a forgotten age. Imagine finding a dinosaur bone in your backyard, except the dinosaur lived trillions of years ago in a universe that technically no longer exists. But the real magic lies in the geometry. Each cycle isn't an exact copy of the last. The universe's shape might warp subtly with each reset, like a spinning top wobbling into a new orientation. Dark energy's grip could loosen, allowing gravity to sculpt fresh structures in the next cycle. Or perhaps the very constants of physics shift slightly, creating universes where stars burn brighter, black holes form faster, or life evolves along entirely new pathways. Penrose's vision isn't just a cosmic Groundhog Day. It's an infinite kaleidoscope where reality reinvents itself with every turn. Critics argue the theory stretches current physics to its limits, relying on untested transformations between infinite scales. Yet if Penrose is right, the universe's true shape isn't a static object but a living thing, endlessly shedding its skin and rising anew. And somewhere in the darkness between cycles, the ghost of a forgotten cosmos might still linger, etched into the fabric of our own. At the atomic level, most crystals follow a simple rule. Their patterns repeat in perfect, predictable symmetry, like tiles on a bathroom floor. But in the 1980s, scientists discovered something that shattered this assumption: quasicrystals. These bizarre structures have orderly arrangements that never quite repeat, blending symmetry with chaos in ways once thought impossible. Now, some physicists suspect this same strange geometry might be woven into the very fabric of spacetime itself, that the universe isn't built on smooth continuity or rigid repetition, but on a cosmic quasicrystal where the rules of order bend without breaking. Picture a medieval mosaic where tiles fit together in star-shaped patterns that never quite align the same way twice. Zoom in close and you'll see local symmetry, five-fold rotations, decagons and spirals, but step back and the overall design refuses to settle into a predictable grid. That's the essence of a quasicrystal. Apply this to spacetime and suddenly the universe's fabric isn't a blank canvas or a pixelated grid, but an intricate, non-repeating tapestry where every region has its own subtle twist on the rules. This isn't just poetic speculation. The math suggests quasicrystalline spacetime could solve some of physics' knottiest problems. Take dark matter, the invisible glue holding galaxies together. If spacetime has a quasicrystal structure, its uneven geometry might naturally create gravitational hotspots, where extra pull emerges without needing unseen particles. Similarly, quantum weirdness, like particles being in two places at once, might just be artifacts of reality's underlying mosaic, with probabilities flickering across non-repeating tiles. Even the speed of light could vary infinitesimally depending on which tile a photon is crossing, like light bending through a hall of mirrors where no two reflections are alike. The most tantalizing clue: quasicrystals thrive where classical crystals fail, in the gaps between perfect order and total chaos. Our universe seems to occupy a similar sweet spot. Too much symmetry and stars might never form. Too little and matter would scatter into randomness, but a quasicrystalline cosmos balances both, creating pockets of stability where galaxies, planets, and life can emerge. It's as if the universe took a page from Penrose's tilings, those famous quasicrystal blueprints, and used them to build reality from the ground up, of course. Proving this theory means hunting for fingerprints in the cosmos. Some researchers scour the cosmic microwave background for anomalous patterns, hexagonal whispers, or pentagonal voids that betray spacetime's hidden scaffolding. Others simulate quantum fields on quasicrystal lattices, watching to see if familiar physics emerges from the noise. And if they're right, the universe's true shape might not be a smooth continuum or a jagged fractal, but a shimmering, chaotic harmony, an infinite mosaic where every piece fits, but no two pieces are ever the same. What if the universe isn't just shaped like a donut? What if time itself loops around its curves like a twisted ribbon, stitching the past to the future in an endless, seamless band? This is the audacious idea behind the time-toroidal universe, where space-time isn't merely bent into a ring, but woven into a structure where time itself spirals back on itself. In this mind-bending model, the cosmos isn't just a static torus of space. It's a dynamic, writhing knot where closed time-like curves allow events to fold back into their own history, like a snake swallowing its tail across eons. The concept springs from Einstein's equations, which already permit solutions where spacetime folds so tightly that time loops become possible. Picture a black hole spinning so fast it doesn't just warp space, it twists time into a whirlpool, creating paths where a particle, or perhaps even a ship, could travel far enough and return to its own past. Now imagine that same principle applied to the universe as a whole. In a time-toroidal cosmos, the fabric of reality isn't just stretched into a giant dome, but it's threaded with invisible tunnels where cause and effect tangle, and the future quietly feeds back into the past. Here's where the implications get dizzying. If the universe has this structure, time travel might not just be possible, it could be inevitable. Not in the flashy Hollywood sense of hopping between eras at will, but as a subtle cosmic symmetry woven into existence. Particles could interact with their own past states, creating feedback loops where events ripple forward and backward simultaneously. Stars might form in patterns that echo their own demise, and even the Big Bang could be entangled with the universe's final moments, like a cosmic Ouroboros where the end is the beginning and the beginning is the end. But how would such a universe even function? Think of a vinyl record spinning on a turntable. The grooves carry the music, but the needle can only move forward. Now imagine the record is twisted into a Möbius strip suddenly. The needle's path loops back, blending the end of the song with its opening notes. In a time-toroidal universe, reality operates similarly, with causality blending into a self-referential symphony. This wouldn't create paradoxes so much as dissolve them, with events adjusting dynamically to maintain consistency, like a river flowing in a circle, always moving yet always returning. Evidence for this wild idea might already hide in plain sight. Quantum entanglement, where particles instantly influence each other across vast distances, could be a microscopic glimpse of time's hidden loops, with correlations threading backward through the cosmic torus. Strange anomalies in cosmic rays or the behavior of high-energy particles might betray the presence of closed time-like curves, their signatures flickering at the edge of detection. Some physicists even speculate that dark matter's elusive nature could stem from particles that don't just move through space, but through time's coiled pathways, appearing and vanishing like ghosts in the cosmic machinery. The most profound consequence, a time-toroidal universe blurs the line between fate and free will. If time loops back, then every choice, every event is both cause and effect, threading a tapestry where destiny isn't a straight line but an intricate braid. It's a vision of reality where the universe doesn't just have a shape, it has a rhythm, a hidden pulse beating across dimensions, reminding us that the past, present, and future might not be separate chapters, but verses in the same infinite song. Deep in the void between galaxies, something strange is happening. Entire superclusters, trillions of stars collectively weighing as much as 1,000 Milky Ways, are streaming through space like leaves caught in a phantom wind. Astronomers call this phenomenon dark flow, and it defies everything we know about cosmic motion. These aren't random drifts, they're coordinated rivers of galaxies all rushing toward the same distant point beyond the edge of our observable universe, as if tugged by a gravitational hand we can't see. The implications are staggering. Either our measurements are catastrophically wrong, or something monumental, something beyond the cosmic horizon, is warping the very fabric of reality on scales we've never imagined. The dark flow was first spotted in 2008, when scientists studying hundreds of galaxy clusters noticed their velocities didn't match predictions. The universe's expansion should scatter galaxies evenly in all directions, like raisins in rising dough. But these clusters were moving with eerie synchronicity toward a patch of sky between the constellations Centaurus and Vela, at speeds surpassing 2 million miles per hour. Even more bizarre, the flow extends at least 3 billion light-years, a quarter of the observable universe's radius, meaning whatever's pulling them must be unimaginably massive. We're talking structures so colossal they make superclusters look like specks of dust, positioned where light hasn't had time to reach us since the Big Bang. What could possibly exert such pull? One chilling possibility is that our universe isn't alone, that beyond the cosmic veil lies another space-time realm, perhaps a neighboring bubble universe with its own gravity, warping ours like a magnet bending iron filings. String theory's brane world models support this, suggesting our universe floats in a higher dimensional space alongside others, close enough for gravitational leakage. Alternatively, dark flow might trace back to the Big Bang's infancy, when quantum fluctuations stretched to cosmic scales during inflation, imprinting the universe with primordial lopsidedness. Picture a balloon inflating with a slight wobble. That asymmetry could now be manifesting as a universe-wide tilt in gravity's tug, the darkest interpretation. Dark flow hints at a cosmic deformity, a fundamental kink in spacetime's geometry that's been hiding in plain sight. Most models assume the universe is isotropic, meaning it looks the same in all directions. But if dark flow is real, it suggests anisotropy, a preferred direction woven into reality's fabric. This could mean the universe isn't a perfect sphere or flat plane, but something more irregular, like a stretched rubber sheet sagging under invisible weight. Certain modified gravity theories even propose that what we're seeing isn't distant mass-pulling galaxies, but space-time itself, draining toward regions of higher curvature, like water spiraling toward a whirlpool's heart. Skeptics argue the dark flow could be an illusion, a statistical fluke or systematic error in how we measure galaxy motions. But follow-up studies, including analyses of the cosmic microwave background's kinetic Sunyaev-Zeldovich effect, have only deepened the mystery. The Planck satellite's data revealed subtle temperature shifts in the CMB aligned with the flow, as if photons were being nudged by the same unseen force. If confirmed, this would mean dark flow isn't just a local anomaly but a cosmological landmark, pointing toward structures so vast they redefine what universe even means. Imagine standing on a shore, watching waves roll in from a sea you can't see. dark flow could be those waves, the gravitational ripples from shores beyond our horizon, hinting at a cosmic geography we're only beginning to map. Whether it's evidence of parallel universes, primordial scars, or a space-time geometry far stranger than we've dared to suppose, one thing is clear. The universe's true shape might not lie within the dome of our sky, but in the unseen currents pulling us toward the dark. Look up at the night sky, and the stars seem scattered randomly like salt spilled across black velvet. But zoom out far enough, and a hidden architecture emerges. Galaxies aren't just floating in isolation, they're strung together in colossal threads, weaving a tapestry so vast it defies comprehension. This is the cosmic web, the largest known structure in existence, and some scientists argue it's not just a feature of the universe, but the very shape of spacetime itself. The numbers alone are staggering. These filaments, made of dark matter and ionized gas, stretch hundreds of millions of light years, connecting galaxy clusters like beads on a necklace. Between them lie the voids, desert regions of near-total emptiness, some so large they could swallow thousands of Milky Ways without coming close to filling up. Together, they form a sponge-like structure with matter concentrated in delicate, interconnected strands. It's as if the universe took a deep breath after the Big Bang and exhaled this intricate lattice, leaving behind a fossilized imprint of its earliest moments. What's mesmerizing is how this web mirrors biological networks. The branching veins of a leaf, the neural pathways of a brain, even the internet's infrastructure, all share this same web-like architecture. Nature seems obsessed with this design, scaling it from the microscopic to the cosmic. But in the case of the universe, the web isn't just a pattern, it might be the backbone of reality. Some theories suggest these filaments are gravity's handwriting, traces of quantum fluctuations from the universe's first trillionth of a second, stretched to cosmic proportions during inflation. The denser regions pulled in matter, while the emptier ones were left behind, sculpting the web we see today. The cosmic web doesn't just shape where galaxies live, it dictates how they move. Astronomers have watched entire superclusters flow along these filaments like rivers following a canyon, funneled by the gravitational pull of the densest nodes. Even dark energy, that mysterious force accelerating the universe's expansion, seems to respect this architecture, widening the voids while leaving the filaments eerily intact. It's a reminder that space isn't just an empty stage, it's an active participant flexing and warping under the weight of its own design. But here's the real mind bender. If the cosmic web is the universe's true shape, then the empty voids might be just as important as the glittering filaments. These aren't just gaps, they're negative space that defines the structure, like the holes in a flute that create its music. Some models even suggest voids could be gateways to stranger geometries, regions where spacetime's curvature twists in ways we don't yet understand. After all, nothing exposes the limits of our knowledge like emptiness. Mapping this web is like trying to trace a city's skyline while standing in a single alleyway. Light hasn't had time to reach us from the web's farthest threads, leaving vast stretches forever hidden. Yet new tools like dark energy surveys and gravitational lensing are slowly pulling back the veil. Each revelation brings us closer to answering the ultimate question. Is the cosmic web just a scar from the universe's birth, or is it something far deeper? The living skeleton of spacetime, still growing, still evolving, still shaping everything we know. Take the smoothest surface you can imagine, a flawless pane of glass, a still pond at dawn, and zoom in closer, a million times closer, past the atoms, past the protons, down to the Planck scale, where distances are so tiny they lose all meaning. Here, spacetime itself isn't serene or solid. It churns, it bubbles, it writhes like a pot of boiling water, with particles and energy flickering in and out of existence so fast they barely register as real. This is the quantum foam, a seething, turbulent layer of reality where the very concepts of here and now dissolve into chaos. And if this foam isn't just a microscopic curiosity but the universe's true foundation, then everything we see, stars, galaxies, even the void between them, might be riding atop an ocean of infinite, frothy turbulence. The idea traces back to John Wheeler, the physicist who coined the term in the 1950s. He realized that at scales 100 billion times smaller than an atom, quantum uncertainty warps space-time into a labyrinth of fleeting wormholes, virtual particles, and mini black holes. Picture a stormy sea frozen in a photograph from afar. It looks smooth, but up close, every wave and ripple tells a story of hidden violence. Quantum foam works the same way. On our scale, space-time seems serene and continuous, but beneath the surface, it's a maelstrom of probability, where geometry itself becomes probabilistic, flickering between countless configurations faster than light can cross a single atom. This isn't just poetic metaphor, it's math. Heisenberg's uncertainty principle dictates that at these scales, energy and time fluctuate wildly, borrowing from the void to spawn particle-antiparticle pairs that annihilate in a blink. Gravity, too, gets in on the chaos, twisting space-time into knots so tight they resemble black holes smaller than a proton, evaporating instantly via Hawking radiation. The foam isn't empty, it's a fermenting brew of potential universes, each bubble a fleeting possibility, a chance for space-time to rewrite its own rules before collapsing back into the froth. The cosmic implications are staggering. If space-time is fundamentally foamy, then the universe's large-scale smoothness, the fact that galaxies can spin in predictable orbits, that light travels straight across billions of light-years, is a miracle of averaging. Like foam in a cappuccino appearing solid from a distance, reality's calm facade emerges from countless microscopic upheavals canceling each other out. But here's the twist. Some models suggest these quantum fluctuations might not just hide in the background. They could leave fingerprints on the cosmos, subtly altering how light travels from distant quasars or how cosmic rays propagate through space. Even black holes might be shaped by this foam. At their event horizons, where gravity stretches space-time to its limits, quantum foam could become a whirling frenzy of virtual particles, some escaping as radiation, others tunneling through microscopic wormholes. This could mean black holes aren't just cosmic vacuums but quantum fountains, their surfaces boiling with space-time itself. And if foam dynamics govern their behavior, it might explain why black holes seem to remember information they swallow, a puzzle that's haunted physicists since Hawking's paradox. But how do you test something so infinitesimal? Some experiments hunt for blurring in high-energy gamma rays. If space-time is foamy, photons traveling across the universe should scatter slightly, like light shimmering through heat haze. Others analyze atomic clocks on satellites, watching for tiny, random fluctuations in timekeeping that could betray space-time's turbulent underpinnings. So far, the evidence is elusive, like trying to hear a whisper in a hurricane, but the search reshapes how we see reality's fabric, the most profound revelation. Quantum foam hints that the universe's shape isn't fixed but probabilistic, a statistical masterpiece where chaos and order dance on the edge of a knife. From the foam's turmoil emerges the cosmos we know, not because it's inevitable, but because amid infinite disorder, stability found a way, and somewhere in that froth, the answers to gravity, time, and existence itself might be bubbling, waiting for us to notice. Black holes are often imagined as perfect voids, spherical pits in space-time so smooth, they're defined by just two numbers, mass and spin. But what if they're messier? What if, like a cosmic chia pet, they sprout invisible, hair, complex outer structures encoding hidden information about their past? This is the startling premise of the hairy black hole theory, and it's not just about black holes anymore. Some physicists now suspect the entire universe might be hairy, its outer edges fringed with intricate geometric patterns we can't yet see. The idea began with a challenge to Einstein's old maxim that black holes have no hair. Traditionally, This meant all black holes were identical twins beneath their event horizons. No matter how they formed, they shed all distinguishing features except mass, charge, and spin. But in 2016, mathematicians discovered exceptions. Certain black holes, when spinning at precise speeds, could sustain permanent distortions in their gravitational fields, like invisible braids or ripples woven into space-time itself. These hairs aren't physical strands but persistent imprints of the black hole's history, whispering secrets about the stars that birthed them or the matter they've swallowed. Now scale this up to cosmic proportions. If black holes can retain hidden structures, why not the universe? Just as a black hole's event horizon traps information inside, our cosmic horizon, the furthest light we can observe, might also hold onto subtle, large-scale hair. These could take the form of gravitational wave fossils from the Big Bang, frozen in spacetime's fabric like grooves in a vinyl record. Or perhaps dark matter filaments, those invisible threads weaving through the cosmos, are the universe's version of hair, tendrils of unseen geometry stretching far beyond what telescopes can capture. The evidence is tantalizingly indirect. When physicists analyze the cosmic microwave background, they find anomalies, unexplained swirls, and asymmetries that don't fit standard models. Some theorize these could be traces of primordial hairs, gravitational imprints from the universe's violent infancy. Others point to bizarre correlations in quasar alignments across billions of light years, as if some hidden structure is orchestrating their orientations from behind the curtain. Even dark flow, that mysterious river of galaxies all moving in sync, might be the universe's hair ruffling in some unseen cosmic wind. But here's where it gets truly radical. If the universe has hair, it challenges our most fundamental assumptions about reality's boundaries. A hairy cosmos isn't just a collection of particles and forces. It's a dynamic entity with memory, its outer layers encoding events from the dawn of time. This would mean the universe isn't just expanding, it's evolving in ways we're only beginning to decipher, its hidden structures whispering stories we've yet to learn how to hear. The search for these cosmic hairs is like trying to trace the outline of a shadow in a pitch-black room. Yet with every anomaly we uncover, every gravitational wave, every skewed galaxy distribution, we get closer to a truth that might rewrite the textbooks. The universe isn't just a smooth, featureless expanse. It's a living, breathing entity, its surface etched with the scars and stories of everything it's ever been. And somewhere in those invisible strands, the keys to existence itself might be waiting, tangled in the dark. Every particle in the universe has a hidden twin, a mysterious doppelganger lurking just beyond the edge of detection. At least, that's the promise of supersymmetry, one of the most elegant ideas in modern physics. This theory proposes that for every known particle, electrons, quarks, photons, there's an undiscovered superpartner with subtly different properties. But here's the cosmic twist. These superpartners might not just be new particles. They could be whispers from extra dimensions, folded so tightly into space-time that they reshape the very geometry of reality. Supersymmetry, or SUSY for short, emerged in the 1970s as a solution to physics' biggest headaches. It elegantly bridges the gap between quantum mechanics and gravity, stabilizes the mass of the Higgs boson, and even provides a candidate for dark matter. But the most mind-bending implication lies in its mathematical backbone. SUSY requires space-time to have more than the usual 4 dimensions. Some theories posit 10 or 11, with the extra dimensions compactified or curled up at scales a billion times smaller than an atom. Picture a garden hose. From a distance, it looks one-dimensional, but up close, you see it's a cylinder. Supersymmetry suggests the universe works the same way, with hidden dimensions coiled into intricate shapes called Calabi-Yau manifolds, their geometry dictating how superpartners behave. These folded dimensions aren't just mathematical abstractions. They could leave fingerprints on the universe's large-scale structure. If extra dimensions exist, gravity, which permeates all dimensions, might leak into them, explaining why it's so weak compared to other forces. Some models even suggest that dark energy, the mysterious force accelerating cosmic expansion, could be the tension of these dimensions slowly unfurling, like a coiled spring releasing energy across billions of years. The shape of these hidden folds might also influence how particles interact, creating symmetries we observe in quantum fields without knowing their higher dimensional origins. The hunt for evidence is a cosmic treasure hunt. Particle colliders like the Large Hadron Collider have scoured energy ranges where superpartners should appear, but so far they've remained elusive. Some physicists argue this means supersymmetry is wrong, while others propose the extra dimensions are curled up even tighter than expected, hiding superpartners beyond our current reach. Meanwhile, gravitational wave detectors listen for echoes of compactified dimensions rippling through spacetime, and astronomers study the cosmic microwave background for anomalies that might betray higher dimensional geometry. If supersymmetry is real, it wouldn't just add new particles to the universe, it would redefine the stage they're dancing on. The universe's true shape might be a multidimensional origami, where every crease and fold holds the key to forces we've barely begun to understand. And somewhere in those hidden folds, the answers to dark matter, quantum gravity, and the universe's ultimate fate could be waiting, tucked just out of sight. What if gravity isn't a fundamental force at all but a side effect of chaos, an illusion born from the universe's relentless slide into disorder? This radical idea, known as entropic gravity, flips our understanding of reality on its head. Proposed by physicist Eric Verland, the theory suggests that gravity doesn't emerge from the curvature of spacetime, as Einstein taught us, but from something far stranger: the universe's inherent tendency toward entropy, the natural progression from order to chaos. Imagine spacetime not as a static stage but as a dynamic, flickering hologram, where gravity arises from microscopic quantum bits jostling for disorder. Like the way heat disperses in a room, not because of some invisible hand, but because nature craves equilibrium. Verland's theory builds on a startling connection between gravity and thermodynamics, the science of heat and energy. In the 1970s, physicist Jacob Bekenstein discovered that black holes have entropy, a measure of disorder directly tied to their surface area, not their volume. This hinted that spacetime might be more like a storage device, with information about its contents encoded on its boundaries. Fast forward to 2010, and Verland took this further, arguing that gravity isn't a force but an emergent phenomenon, a statistical side effect of entropy's drive to maximize itself. Picture a crowd of people in a stadium. Individually, they move randomly, but collectively, their motion creates waves that ripple outward. Gravity, in this view, is the cosmic equivalent, a macroscopic pattern emerging from microscopic chaos. The implications unravel the fabric of reality. If gravity is entropic, then spacetime itself might be an illusion, a holographic projection of deeper quantum interactions happening at the universe's edges. This would mean the universe's shape isn't dictated by geometry alone, but by thermodynamics, with galaxies and black holes forming where entropy gradients are steepest, like ice crystals growing in the cold. Even dark matter, that enigmatic cosmic glue, could be an artifact of this entropic dance, a mismatch between our Newtonian expectations and the universe's true, disorder-driven mechanics. Critics argue that entropic gravity remains untested, but Verland's ideas have already reshaped the conversation. Some theorists are exploring how entropic effects could explain galaxy rotation curves without invoking dark matter, while others are simulating emergent spacetime in quantum computers. If proven, this theory wouldn't just rewrite textbooks, it would redefine the universe's very architecture, revealing a cosmos where gravity, shape, and even time itself are fleeting whispers in a vast thermodynamic symphony. And somewhere in that chaos, the true nature of reality might be hiding, not in the equations of forces, but in the silent, relentless march of entropy. Imagine the universe isn't smooth and continuous, but built like a diamond, a vast, shimmering lattice where every atom of space-time locks into an intricate crystalline grid. This is the bold vision of the crystalline universe theory, where the fabric of reality isn't a featureless expanse but a structured framework, riddled with tiny imperfections that might hold the key to dark energy and the cosmos' runaway expansion. The idea reimagines space-time as a quantum spin lattice, a cosmic scaffold where each point vibrates with energy, creating the illusion of smoothness at our scale. Just as real crystals have defects, gaps, or misalignments in their atomic structure, this cosmic lattice could harbor its own flaws. These defects wouldn't be flaws at all, though. They might be the engines driving the universe apart, creating repulsive forces that mimic dark energy. Picture a frozen lake with cracks beneath the ice. As the cracks widen, the surface stretches. In the cosmic version, spacetime's defects could be generating the same effect, pushing galaxies away from each other like invisible levers prying the universe open. What's fascinating is how this ties to real-world physics. In condensed matter science, crystals under stress exhibit emergent phenomena, unexpected behaviors like superconductivity or strange metallicity. If spacetime is a quantum crystal, its defects could produce equally exotic effects. Some models suggest these imperfections might concentrate dark energy into domains, like bubbles of pressure in a carbonated drink, explaining why cosmic acceleration isn't uniform but varies subtly across the void. Others propose that the lattice's vibrations could manifest as dark matter, with defects acting as gravitational anchors that distort the motion of galaxies. The crystalline universe doesn't just reshape our understanding of dark energy, it redefines the nature of spacetime itself. Einstein saw gravity as the curvature of a smooth continuum, but in this model, gravity might emerge from the lattice's collective vibrations like sound waves traveling through a diamond. This could resolve one of physics' deepest puzzles: why quantum mechanics and general relativity refuse to reconcile. If spacetime is granular, not smooth, their clash might just be a mismatch of scales, like trying to describe a symphony using only the notes of a single instrument. Evidence for this theory could lie in the cosmos' oldest light. If spacetime has a crystalline structure, light traveling across billions of years might pick up subtle distortions, like a prism splitting sunlight into colors. Astronomers have already spotted anomalies in the polarization of the cosmic microwave background, swirls and spikes that don't fit standard inflation models. These could be the universe's graininess imprinting itself on photons, a faint fingerprint of the lattice beneath reality's surface. Yet the most mind-bending implication isn't about what the universe is, but what it implies for existence itself. A crystalline cosmos suggests that reality isn't fluid but modular, built from indivisible units of spacetime that click together like cosmic Legos. This would mean there's a fundamental resolution to the universe, a pixel size below which zooming further reveals nothing because there's nothing smaller to see. Whether this lattice is the key to dark energy or a dead end, it forces us to confront a staggering possibility. The universe might not just have a shape, but a structure, an architecture hidden in plain sight, waiting for us to decode its blueprint. What if the universe doesn't just fade into cold darkness? What if it tears itself apart in a cataclysmic finale, shredding reality atom by atom? This isn't science fiction. It's the spine-chilling prediction of phantom energy, a hypothetical force even more relentless than dark energy, capable of stretching spacetime to its breaking point. In this nightmare scenario known as the Big Rip, the universe's expansion doesn't just accelerate, it becomes ferocious, overpowering gravity, then electromagnetism, then even the nuclear forces holding particles together. The cosmos wouldn't just end, it would unravel violently, its very fabric fractured into oblivion. phantom energy takes dark energy's playbook and cranks it to 11. While dark energy drives the universe's expansion at a steady pace, phantom energy grows stronger over time, like a snowball rolling downhill, gathering mass and momentum until it's unstoppable. Picture a rubber band stretched tighter and tighter. Eventually, it snaps. Now imagine that rubber band is space-time itself, and the snap obliterates galaxies, stars, and eventually the atoms in your body. According to some models, this could happen in as little as 22 billion years, a blink on cosmic timescales. The universe wouldn't just expand, it would disintegrate, leaving behind a desolate, infinite void where even light can't escape the stretching. The mechanics are as brutal as they are elegant. First, phantom energy would shred the cosmic web, severing the gravitational threads that bind galaxy clusters together. Next, it would rip apart individual galaxies, flinging stars into the abyss like sparks from a wildfire. Then, as the expansion reaches nightmarish speeds, planetary systems would be torn from their orbits. In the final moments, planets, molecules, and even atomic nuclei would be ripped apart, their components scattered across a space-time stretched so thin it loses all meaning. The universe wouldn't just die, it would be erased pixel by pixel like a corrupted file dissolving into static. But here's where the mystery deepens. Phantom energy isn't just about destruction, it reshapes the universe's geometry in horrifying ways. Most dark energy models assume a flat or gently curved cosmos, but phantom energy could warp space-time into a phantom singularity, a state where the universe's density and expansion rate become infinite. This isn't a black hole singularity hidden behind an event horizon. It's a singularity that engulfs everything, everywhere, simultaneously. Space wouldn't just expand, it would hyperinflate like a balloon blown up until its surface vanishes into transparency. The universe's shape wouldn't just be distorted, it would be annihilated, replaced by a mathematical abstraction where distance and time lose all coherence. Is there any way to spot the warning signs? Some theorists suggest phantom energy would leave fingerprints in the redshift of distant supernova, appearing anomalously bright as space stretches faster than light can traverse it. Others hunt for distortions in the cosmic microwave background, subtle asymmetries that might betray phantom energy's growing dominance. So far, the evidence is ambiguous, but the search forces us to confront a haunting question. Is the universe's fate a slow fade or a shattering crescendo? The Big Rip isn't just a theory, it's a cosmic horror story written in the language of physics. Yet it also reveals something profound. The universe's shape isn't set in stone. It's a dynamic, evolving thing, capable of violence as much as serenity. And if phantom energy is real, then the cosmos we know, with its galaxies, its stars, its fragile islands of life, isn't just temporary. It's ephemeral, a fleeting pattern in a space-time destined to dissolve like sand in a storm. Imagine if the entire universe around you, every star, every memory, even the screen you're staring at right now, wasn't real. Instead, it all just spontaneously formed from random quantum fluctuations, assembling for a fleeting moment before dissolving back into chaos. This is the chilling premise of the Boltzmann-Brane paradox, a thought experiment that shakes the foundations of cosmology and forces us to confront a terrifying possibility. If reality is shaped by randomness, even the most fundamental truths we take for granted might be illusions. The paradox comes from 19th century physicist Ludwig Boltzmann, who realized that entropy, the universe's tendency toward disorder, doesn't enforce perfect uniformity. In an infinite cosmic expanse, sheer randomness will occasionally produce order by pure chance, like shaking a box of sand until a sandcastle briefly forms. Given enough time, even something as complex as a fully formed human brain, complete with false memories of a lifetime, could materialize from the void. And statistically, in an eternal, infinite universe, these Boltzmann brains should vastly outnumber real, evolved minds like ours. So why aren't we one of them? This isn't just philosophical wordplay, it's a direct challenge to how we understand the universe's shape and history. If the cosmos is truly infinite and eternal, then the orderly universe we perceive should be vanishingly rare compared to the number of random, self-aware fluctuations bubbling up in the void. The fact that we observe a coherent, structured reality suggests something is fundamentally wrong with that picture. Either the universe isn't infinite in time or space, or there's a deeper structure, like inflation or quantum gravity, preventing such chaotic fluctuations from dominating existence. Now connect this to cosmic geometry. A flat, infinite universe would be the perfect breeding ground for Boltzmann brains, with endless time and space for random order to emerge. But a closed, spherical cosmos that eventually collapses back into a big crunch, that finite timeline limits the opportunities for statistical anomalies to overtake reality. Similarly, if the universe is a holographic projection, the underlying code might enforce consistency, preventing rogue fluctuations from hijacking our perception. Even the multiverse theory offers a grim twist. In an endless sea of bubble universes, most might be Boltzmann chaos, with only a rare few stable enough for life to evolve normally. The implications ripple across physics. If Boltzmann brains are more probable than real observers, then our entire scientific method, built on repeatable observations, could be built on sand. How could we trust any experiment if our instruments are memories? Even the laws we measure might be temporary glitches. Some theorists argue this very paradox is evidence that the universe must have a beginning and end, a finite shape that prevents such statistical nightmares. Others propose that quantum decoherence, or the holographic principle, acts as a cosmic firewall, stabilizing reality against these rogue fluctuations. Yet the most unsettling possibility isn't that we're Boltzmann brains, it's that the paradox reveals how little we truly know about the universe's architecture. The fact that we can imagine our entire existence being a fleeting fluctuation means our cosmic maps are still missing something fundamental. Whether it's hidden dimensions, an undiscovered law of quantum stability, or a cosmic shape we've yet to fathom, the Boltzmann brain paradox isn't just a curiosity. It's a flashing warning sign that reality's true form might be stranger and more fragile than we ever dared to suspect. Now we arrive at the most unsettling possibility of all. What if the universe doesn't have a fixed shape at all, but shifts and twists depending on who's looking? This is the radical core of the observer-dependent universe theory, where consciousness itself isn't just a product of the cosmos but an active participant in its design. At the heart of this idea lies one of quantum mechanics' most baffling experiments, the double-slit test. Fire particles like electrons at a barrier with two slits, and they behave as waves, creating an interference pattern on the detector screen unless you try to observe which slit they pass through. The moment you measure, the wave function collapses and the particles revert to behaving like discrete objects. It's as if reality changes its behavior based on whether it's being watched. Scale this up to the cosmos and the implications are staggering. If quantum systems remain in superposition, existing in multiple states simultaneously until measured, could the entire universe be in a similar state of ambiguity? Some interpretations suggest that without observers, space-time might not even have a definite geometry. The universe could be a quantum foam of potential shapes: flat, spherical, toroidal, all coexisting until conscious beings like us interact with it, forcing one configuration to crystallize into reality. This isn't just philosophy, it's a mathematical possibility embedded in the equations of quantum cosmology. The most famous proponent of this view was physicist John Wheeler, who proposed the participatory universe model. He imagined existence as a self-excited circuit, where observers in the present retroactively influence the universe's past state through the act of measurement. Picture a cosmic game of 20 questions where the universe only chooses its history when questioned. In this framework, the Big Bang's initial conditions, and thus the universe's shape might not have been fixed until life evolved to observe them. It's as if the cosmos was waiting for someone to ask, "What are you?" before deciding on an answer, but here's where it gets even stranger. If consciousness plays a role in defining reality, does that mean isolated galaxies in empty voids exist in a hazy superposition until observed, and who or what counts as an observer? Some theories propose that any interaction, even between particles, constitutes a measurement, collapsing quantum possibilities into concrete reality. Others argue that true observation requires self-aware entities, implying the universe might fine-tune its structure around islands of consciousness like a cosmic ecosystem nurturing its own perception. Critics dismiss this as solipsism dressed in equations, but the math resists easy dismissal. Quantum decoherence, the process by which superposition breaks down, shows that classical reality emerges from quantum weirdness through interaction with the environment. On cosmic scales, this could mean the universe's geometry isn't absolute but relational, like a quantum version of Einstein's relativity. The shape of space might not be a standalone property but a network of relationships between observers and the observed, forever in flux. The darkest interpretation: if consciousness truly molds reality, then the accelerating expansion of the universe driving galaxies beyond the horizon of observation could have existential consequences. As more of the cosmos becomes unobservable, those regions might revert to quantum indeterminacy, their geometry dissolving like a dream upon waking. In this view, the universe's fate isn't just a slow heat death, but a gradual unraveling of its very structure, as Chinese letter of observers shrinks and reality loses its grip on itself. Whether this theory is profound or preposterous, it forces us to confront a humbling truth. The universe's shape might not be written in the stars, but in the act of looking at them. And somewhere in that entanglement between consciousness and cosmos, the answers we seek might not be out there at all, but in here, in the very act of asking the question. From the cosmic donut to the holographic illusion, from the fractal tapestry to the crystalline lattice, we've journeyed through mind-bending landscapes where the universe's true shape defies everything we thought we knew. Each theory isn't just a wild guess, it's a doorway to an entirely new way of seeing reality. The flat universe whispers of infinite doppelgangers, the big rip warns of spacetime's violent unraveling, and the toroidal cosmos offers a map where every path loops back on itself. Even the Boltzmann brain dares to ask, are we the architects of our own illusion? These ideas don't just challenge science, they rewrite the story of existence. If the universe is a simulation, then every star, every atom is just code in an unfathomable program. If it's a white hole's echo, our entire history might be the aftershock of another reality's collapse. And if consciousness itself molds space-time, then the cosmos isn't just something we observe, it's something we shape with every question we ask. So here's the real mystery: which of these shapes feels right to you? Are we floating on a brane in a higher dimensional sea, or trapped in the event horizon of a black hole's rebirth? Could the cosmic web be the universe's skeleton, or is reality a flickering quantum foam bubbling with possibilities? The answers aren't just hidden in equations, they're written in the night sky, waiting for us to look up and wonder. Drop your favorite theory in the comments below. Do you side with the holograms, the donuts, or something even wilder? And if you're hungry for more cosmic mysteries, hit subscribe. The universe is far stranger than we've imagined, and together we're just getting started.